Welcome back. In our last episode, we explored the big picture of how ChatGPT works, from embeddings that give meaning to tokens to self-attention layers that shape predictions and finally to output probabilities. Today, we're focusing on the model's secret sauce, the math behind self-attention. This is the mechanism that allows the model to understand the relationships between words, such as figuring out that in the sentence, the cat ate the fish because it was hungry. The word ate refers to the cat, not the fish. By the end of this episode, you will understand exactly how self attention works, why it is so powerful, and how it forms the foundation for everything ChatGPT can do. When the model processes a sentence, it first converts each token into a vectors, which is a numerical representation that captures its meaning in a multi-dimensional space. These token vectors are then passed into the self-attention mechanism. In this stage, each word compares itself with every other word in the sentence, assigning attention weights based on how relevant they are to its meaning. This process allows the model to determine which words should receive more focus when predicting the next token. In self-attention, each token is turned into three separate vectors such as query, key, and value. The query represents what this token is looking for in the other tokens. The key represents what this token contains that others might find useful. And the value is the actual information it will pass along once the right match is found. These vectors are created by multiplying the original token embedding by three learned weights matrices, allowing the model to determine how much each token should pay attention to the others. Next, we compare every query with every key using a dot product. This gives us a score for how the relevant each other word is to the current one. Here is the formula how to find the scores of the tokens using the dot product of query matrix with the transpose of key divided by the square root of the dimension space of the keys, where Q is the query matrix, the key power T is represented the transpose of the key matrix, and dk is dimensions of the key vectors used for scaling. So the qk computes the dot product between every query and every key, giving a measure of similarity or relevance. Then dividing by the square root of the vector dimension dk prevents the dot product from growing too large, which stabilizes training and improves gradient flow. Here is the step one, the dot product for similarity. The dot product is a way of measuring similarity between two vectors. In the context of self-attention, a higher score means a stronger relationship between the words. For example, in our earlier sentence, the vectors for it and cat produce a higher score, indicating that they are more closely related in meaning. We begin with two tokens. Each token has a query vector and a key vector. That is 1, 1, 1, 0 is the key matrix for the same two tokens, and 1, 0, 0, 1 is the query matrix for two tokens. Here, the dimensional space of the key is 2 because that is the vector length for each token. Next, take the transpose of the key. This prepares us to compare every query with every key using the dot product. So in this case, the transpose looks the same with the original matrix of the key, because in the transpose, you just turn the columns into rows. So the columns are 1, 1, and 1, 0. So when you turn the first column into the first row, 1, 1, that's the same 1, 1. And when you turn the second column into the second row, 1, 0, 1, 0. So we get the same result with the key matrix. All right, now compute the raw similarity scores of the dot product of the query matrix by the transpose of key. So we multiply the Q by the transpose of K to obtain raw similarity scores. Each entry is a dot product between one query and one key. Each row of the score matrix shows how much the corresponding focuses on or attends to every key in the sequence. So let us take the first query vector, that is 1, 0. So we just multiply the first row of the query matrix with the first row of the key matrix, that is 1, 1. So in this case, we just multiply 1 times 1 plus 0 times 1. So when you multiply 1 by 1, that is 1, plus 0 by 1 is 0, that is 1. All right. So in this case, we get 1 in the result. Again, we multiply the first row in the query matrix with the second row in the key matrix. That is, the result is the same. That is 1. All right. Now let's go to the second row in the query matrix, 0, 1, 0, 1, multiplied by 1, 1, 1, 1. So 0 multiplied by 1 is 0, plus 1 multiplied 1 is 1. So we get 1. That is right. Finally, we multiply the second row in the query matrix with the second row in the key matrix, that is 0, 1 by 1, 0. So 0 by 1 is 0, plus 1 by 0 is 0. That is 0. So the dot product of query matrix by the transpose of the key matrix is 1, 1, 1, 0. So this is the raw similarity score matrix. Each row is equal how much the tokens query matches every key. All right, now that we have the raw similarity scores from the dot product, the next step is to scale them by dividing the square root of the dimension of the keys. Because without scaling, these values can grow too large as the vector dimension increases, and that makes the softmax function unstable. So the rule is simple. Since the dimension of the key matrix is 2, so the square root of the dimension space of the key is approximately 1.414, and we already calculated the similarity scores of the dot product, that is 1, 1 and 1, 0. Now we divide these similarity scores by the square root of the dimensions of the keys. So here we divide by 1.414, and we obtain 0.71, 0.71, 0.71, and 0. The raw scores matrix we just calculated from the dot product is 1, 1, 1, 0. So the first three ones are just divided into this, and we obtain the first three 0.71, and the last one is 0. So after scaling, so this is our score matrix. Row 1 shows token 1 equally related to both tokens 0.71 each. Row 2 shows token 2 relate to token 1 more strongly than itself. That's 0.71 versus 0. All right. Once the scores are scaled, the model applies the softmax function. Softmax transforms these raw numbers into probabilities that always add up to 1. So the result will be 1. This step highlights the most relevant connections while keeping less important ones small but non-zero. So our scaled scores are this one. We calculated in the step 2. Now let's work it out step by step. Step 1 is just take the exponential of each value. We just find the exponential of each value of the scaled scores. For example, e the power of 0.71. That is approximately 2.03. So the same is for the all the three tokens, and the last one is 0. So we just use e the power of 0 is uh, 1. That is the rule of exponentiation. All right. Once we calculated the exponential of each value, we just add the result of each value, and we get 7.09. Then in step 3, divide each exponential by the denominator. So the denominator is 7.09, and we divide each exponential value by this number, and we get 0.29 for the three tokens and 0.14 for the last token, because 1 divided by 7.09. All right, so the final softmax probabilities are 0.29, 0.29, 0.29, and 0.14. So this is our final softmax probabilities. So this means the model distributes most of its attention equally across the first three words, while still giving a smaller weight to the last one, that is 0.14. These numbers are what guide the attention mechanism in deciding where to focus. Now let's move on to step 4. After softmax, we now have attention weights for each word. So these weights tell us how much each word should contribute to the final representation, of the target word. The next step is to take a weighted sum of the value vectors. Here's how it works. Each word already has its value calculated from the softmax. So this is our example of the attention weights where we calculated in step 3 by applying the softmax. And this is the output. We just calculate the output by summing up the attention of each token with the value of each token, where AI is an attention weight for word I, VI is value vector for word I. So in our example, 0.29 dot V1, which means multiply by V1, value 1, plus 0.29 times value 2 plus, and so on. So this is the final output of the token. Finally, we add them all together, look like this, And for our example, the attention weights uh, were this one. So the model combines the value vectors in this exact ratio. The result is a new vector that represents the target word, which enriched with context from the other words in the sentence. This is what makes self-attention powerful. The representation of a word is not fixed, but dynamically adjusted based on its relationship with every other word in the sentence. Now let's make this concrete with numbers. We just suppose each value vector is two-dimensional, 1, 0, 0, 1, 1, 1, 0, 0, just for simplicity. And from the softmax, we already calculated the weighted attention. The attention weights were 0.29, 0.29, 0.29, and 0.14. Now we multiply each value by its weight. So 0.29 multiply with 1, 0, value 1, 0.29 times V2 is 0, 0.29, 0.29 times 1, 1 is 0.29, 0.29, and 0.1 times 0, 0 is, that is 0, 0. Finally, we add them all up, so we get 0.58, 0.58. The output for this word is the new vector, that is 0.58, 0.58. This shows how the word's meaning has been updated by blending information from the other words, weighted by their relevance. So far, we have looked at attention as if there were only one set of theories, keys, and values. In reality, transformers use multiple attention heads running in parallel. Each head looks at the sentence in a slightly different ways. One head may focus on short-range grammar, another on pronoun resolution, and another on long-range context. So the outputs from all these heads are then combined and projected into a single vector. So this multi-head setup allows the model to capture many types of relationships at once, giving it a richer and more flexible understanding of language. Now let's wrap up what we have learned in this episode. At the core of self-attention are the queries, keys, and values. The mechanism works through four precise steps. The first step is the dot product. Then once we get the score of the dot product, we scale by dividing the square root of the dimensions of the keys. And then we apply the softmax to get the weighted attention. Softmax converts them into probabilities, and finally, a weighted sum produces the output. But the real power comes from using multiple attention, that is multi-head attention, in parallel. Each head focuses on different relationships and patterns, and together they give the model a rich and more flexible, understandable language. This process is the reason why ChatGPT can capture context so effectively and generate meaningful responses.